doing a lot of really great work. Thanks, Anthony. He's doing a lot of really great work related to what we're doing here specifically, and it'll be a really great opportunity for him to present his work. Before jumping into a little bit about the rest of this talk today, I just wanted to give kind of the standard set of announcements. We have our seminar schedule will be updated. I'll say a little bit more on that on our website. You can find that on the top list. If you haven't joined our mailing list, please do so. We'll be sending out more information about the upcoming workshop this summer and other information. And then, like all of our presentations, we will be recording this. We are recording this and we'll be uploading it to YouTube, so you can come back to our YouTube channel and watch them more there. And just to give a quick plug before jumping in, we are having a workshop this summer in Germany, so please make sure to register if you're interested. The URL for the workshop is here, and we'll make sure to kind of post that in the Zoom chat so that you can access it here. And we're really excited for Grant to be talking. This is the first, Grant will be giving the first of a two-part seminar series. We'll be talking about data mining techniques in producing empirical maps. And then next month, it will be a talk given by, combined talk given by Harry Arnold and Anthony Shiola of APL, where they will take these data mine maps that Grant will be talking about today and trying to ingest those into first principle models. So without further ado, I'll pass it off to Anthony for the introduction.
All right, hello everyone, welcome back. Just a quick reminder, as always, please keep yourself muted. And then also, Grant is happy to take questions during the talk. So if you have a question, just feel free to raise your hand or put it in the chat, and we'll make sure that Grant sees your question. So Grant is a staff scientist here at APL. His research interests include empirical magnetosphere modeling, as well as investigating magnetospheric dynamics during storms and substorms. And as Adam said, this will be part one of a two-part talk, and I'll let Grant get right into it. So thanks very much for joining us today.
Yeah, thanks for inviting me to give this talk. Let's see, I will try to share my PowerPoint here. Okay. Am I sharing the right presentation screen or not?
We see PowerPoint, but it's not in presentation mode yet.
Still not?
No, nothing's changed on our screen, at least.
Why don't I? We'll have to move.
Huh.
It's still not?
No, not yet.
Unfortunately, when you click that button, it just stays on the presenter notes screen.
Okay. Let me try sharing again.
I tend to have better luck if I go to slideshow first and then choose the screen to show. All right. Now it's in presenter mode. Yeah. Okay, that looks good.
Perfect.
That was good. Okay.
Nice.
I had too many screens open, I think.
Do you mind just jumping back and forth between two slides to make sure that's working well?
Yeah, sure. Does that look good?
Yep. All right, we're all set.
All right, so a little bit of an outline of my talk. There's thanks for Anthony and Adam introducing my talk here. So like they said, this is a two-part series. So this will be part one, data mining based empirical reconstructions of substorms. And then next month will be part two, which will be how Harry and Anthony are using the results of my data mining reconstructions to try to guide some first principle simulations. And this is what we call gray box modeling of Earth's magnetosphere. So a brief outline of my talk. I'm going to give an introduction, overview, and methodology. Normally, I try to kind of fly through this stuff, but I figure given the kind of audience of this GeoDAWG workshop, it might be interesting if I kind of delve into some of these methodological slides here. So, and then I'll jump into my storm reconstructions, talking about the empirical pressure, and then finally substorm reconstructions of the magnetotail, and how we are trying to resolve the X line in the magnetotail during substorms. And I'll briefly go into how we can also combine our storm and substorm models into one coherent model of the magnetosphere. So a little bit of an introduction is, so first is, what is a gray box model? And so a gray box model is a term that is trying to capture the combination of a white box model or first principles or physics-based model with a black box or data-driven or empirical model. So examples of white box models in the magnetosphere would be the whole, this whole range of different MHD simulations. So LFM and Gamera and BATSRS and Open GGCM. But then there's this other class of first principle models called kinetic models. Some of the commonly used ones are the RCM and CME models that describe the ring current region. And then there's also particle and cell codes that are often used in the magnetotail. But the point is, there's some limitations to these type of models. They have to make assumptions about what physics to include in these models. For example, MHD doesn't describe particle effects, but there's also numerical issues. There's an important physics that they're trying to describe, but it may span a large variety of orders of magnitude range of scale sizes and time scales. So that requires finer and finer grids and smaller time steps to try to resolve these wide range of scale sizes. So a lot of work has been done to couple various white box models together. So MHD models are often paired with a realistic ionosphere. They are often paired with ring current models like the RCM model, for instance. But we're going to present a different approach over these next two talks, which is a gray box modeling, which is basically combining a white box with black box models. So what are black box models? These are data-driven or empirical based. It's often used in the context of machine learnings and often used to describe artificial neural networks, or are often called black box models. In the magnetosphere, empirical magnetic field models, there's empirical electric field models, and a variety of different empirical models for radiation belts, and the ionosphere exist across the domain. But these also have limitations. The solutions may not be consistent with known physics. And there's also this principle of garbage in equals garbage out. So the models are only as good as what the underlying data that have been used to train them. And a gray box model is just simply combines white box and black box models together. There's many different flavors because there's many different ways you can combine these type of models. So black box models can be inserted within a white box, or simulated data can be added to, let's say, an artificial neural network to try to expand the amount of database that the model can be trained on. So these are kind of vague terms, but this is just kind of a 10,000 foot view of what a gray box model is. So you might ask, these first principle models have made drastic advancements in recent years. Here's an example of a Gamera simulation showing some of all these cool features that it now resolves, like KH instabilities and these earthward flowing bubbles that penetrate into the inner magnetosphere. And but MHD models have limitations. One is the isotropic or isentropic equation of state. So basically, this is that an equation of state in MHD models can't account for the particle gradient curvature drifts that really formulate the ring current during storms. That's why they have to be coupled to kinetic models, such as the RCM model in the inner magnetosphere. But another issue is the idealized Ohm's law. So MHD simulations often rely on numerical resistivity to kind of initiate reconnection both on the day side and within the magnetotail. So the part of the problem with this, and Harry, and we'll go more into detail with this next week, but this often reconnection occurs much closer to Earth than what is observed in the data. Another problem is the equation of motion with the isotropic force balance. So embedded thin current sheets play a critical role, particularly in the substorm growth phase. And recent theory is starting to indicate that these very long, thin current sheets that exist in the tail are really the result or can need to be described using the anisotropic and agiotropic terms in the pressure tensor, and that isn't efficiently described in MHD simulations. So these are just some example of limitations that exist in current MHD models. And what I want to demonstrate is that these issues can potentially be mitigated using empirical magnetic field models, but until very recently, these models were just too simple or too rudimentary to be appropriate for ingestion into MHD because of their kind of custom tailored and ad hoc nature. And I'll go more into that in a bit. So brief overview of storms and substorms. What I'm showing down here are two geomagnetic indices. The first one on the left, this black line, is the SIMH index. So this is often used as a proxy for storms. So, so storms are measured at mid to low latitudes. And as you can see, this particular one takes place. This is a fairly intense storm, about a minus 100 nanotesla. You can see it's quite complex. It has a series of dips first, and then we get into the main phase and then the recovery phase. So storms occur over a couple days often. They're often the result of a coronal mass ejection, a CME, or a co-rotating interaction region, CIR, that get carried by the solar wind and causes a prolonged southward interplanetary magnetic field which allows enhanced convection, which ends up enhancing the ring current. In kind of contrast, the storms are substorms. So these substorms were initially kind of thought of as building blocks to storms, but it's no longer, that picture is now no longer really accepted. But these are often observed at high latitude magnetometer stations near local midnight. They are much shorter in duration. So these are captured by this AL index that I'm showing here in orange. And you can see that they're several hours long at most. And so what I'm showing here are distinct phases of these different substorms embedded within this storm. So this is important to note that storms and substorms occur at the same time, that concurrently and in the same, often the same spatial regions. And they're captured by these global geomagnetic indices. So SIMH and for storms and AL for substorms. And we often frequently use supermag data, and they have their own analogs, the SMR index for storms and the SML index for substorms. So I might interchange these indices with their supermag equivalents during this talk. A brief introduction to empirical magnetic field models. So the way these models have kind of worked is you start with this cartoon picture of the magnetosphere, has these variety of current systems. So the magnetic field can be related to the current density via the magnetostatic form of Ampere's law shown here. So basically what we're trying to do is find an analytical expression for each of these current systems, right? So the total external magnetic field can be decomposed to the magnetic field to each of these current systems. So this is termed the modular approach to magnetic field modeling. So what you end up getting is each of these current systems has a linear amplitude coefficient that needs to be fit to the data. but they also contain these nonlinear parameters, such as these often define the morphological structure of the current system. So an example would be the current sheet thickness. So we have these two sets of linear amplitude coefficients, and nonlinear parameters that we then want to constrain to the available magnetometer data. And before I dive into our current model, I want to really contrast. So these empirical magnetic field models have existed well all the way back into the 70s. And they have continued to evolve over time. But this new era of empirical magnetic field modeling, which is supported by modern data mining approaches, are really different than your classic kind of Sigonyenko style empirical magnetic field model. So here I'm showing an equatorial slice of the TSO5 model. So this is one of the most commonly used empirical models versus the new generation, the TSO7 model, which was the first model that really utilized this data mining approach. And the motivation behind this is to allow the data to dictate their morphology as well as its evolution in time, and not hand-built functions, ad hoc functions. So you can see in the classic approach, you take each of these current systems and you try to figure out a way to describe that current system analytically. But what that results in is very kind of hand-built. You can see the tail current module here, the partial ring current module, the symmetric ring current module. Whereas the TSO7 approach utilized a general basis function expansion. I'm going to get into it more, but it doesn't have a predefined spatial structure in this equatorial plane. And you can see how it still resolves these main features, main current systems, but it does so in a much more natural way. It's really allowing the data to dictate what this morphology is, not kind of our hand-built cartoon picture of what the magnetosphere looks like. And the cool thing about this new approach is it makes these models really amenable to scientific investigations, because we can really kind of capture what is in the data. So I want to briefly outline the general methodology. So first, we have a database of magnetometer data, and then we use a data mining approach. We use the K nearest neighbor approach to subset a small portion of the entire database by assuming that we can characterize the state of the magnetosphere using substorm indices, storm indices, the solar wind electric field parameter, and the derivatives of the indices. That's really important to capture the state of the magnetosphere. And then the idea is we data mine our entire magnetometer database to get about 1% of the magnetometer data that is most similar to the moment in time we're trying to model. We fit our empirical model, and then that gives us the 3D magnetic field throughout the magnetosphere. So to go a bit more into the methodology here, I'm going to describe the equatorial currents. So like I said, instead of using these kind of hand-built modules to describe the equatorial currents that exist in the magnetosphere, the TSO7 approach used the general solution to an arbitrary current disk. So if we write down Ampere's law for this thin current sheet, you end up getting, you can represent the magnetic field by a scalar potential if you're above or below it. And then this is basically out of Jackson E&M type stuff here. So you can get this scalar potential, which is just the general solution to this current sheet. We can then convert that to a magnetic vector potential. And then we represent all the equatorial current systems, so the symmetric ring current, the partial ring current, and the tail current, using this basis function expansion, right? So this is just the general solution for the magnetic field due to an arbitrary current disk or current sheet. And when in developing our substorm model, we then added 2 such current sheets to try to capture an embedded thin current sheet, particularly for the substorm growth phase. For the field aligned current structure, we use these conical currents that were derived by Sigonyenko in the late 90s and early 2000s. So these are very rigid in latitude. Oops. And they are bent to then approximately follow the dipolar field lines. These introduce additional nonlinear parameters that allow these systems to expand and contract. And we use a total of 16 such systems in our current version of the model. So here was the original TS07 conical current system as seen at the ionosphere level. And you can see just how rigid this is in its latitudinal structure. So it uses a Fourier series for the longitudinal structure, but at the expense of this rigid solution in latitude. And what we realized is we can just take several of these systems. Like I said, we now use 16, kind of overlap them in latitude, and we can mimic an expansion type solution in latitude, which gives a much more closely matches this kind of complex morphology seen in the real field aligned current system, including this spiral shaped pattern associated with the harangue discontinuity. There's additional effects that are also built into the model, such as the dipole tilt effects that distort and deform the equatorial current system. So there's 3 such effects: bending, as you see here, warping, which kind of warps the warps the neutral sheet, and then twisting caused by a non-zero IMF BY. So these are kind of built into the structure of the model. And then also we consider dynamic pressure effects. So this is called the self-similarity rescaling that's applied to most empirical magnetic field models of the Earth and other planets. So it assumes that the whole system is expanding and contracting based off of changes in the dynamic pressure. And all current systems then get expanded and contracted. And to explicitly build it into the structure of the model, we replaced the amplitude coefficients here with this expansion using as a function of the dynamic pressure explicitly. So this is how we account for dipole tilt and dynamic pressure effects in the model. All right, so I want to, so that kind of summarizes the model morphology, how the actual current systems are structured, but that just is for a particular snapshot in time. So how do we then describe the dynamical evolution of the magnetosphere? And again, the motivation behind this is to allow the data to dictate the time evolution and not predefined functions. So the idea is that for a given moment of time, we can data mine our entire magnetometer database for a small subset, like I said before, about 1% of the data that is most similar to the point in time we're trying to model. And then the model is refit for each moment. So this whole process of data mine the magnetometer archive, get a subset of that data, fit the empirical magnetic field model. There's our global snapshot for that moment in time. And then we do that again for the next moment and the next moment and the next moment. And that gives us the dynamical evolution of the magnetosphere. So the data mining technique we use is this KNN method. It's mostly used as a pattern classification algorithm. And we've kind of turned it on its head and are using it as a data mining approach. So the idea is that we're trying to characterize the complex state of the magnetosphere using a small finite dimensional state space, right? And the idea is that as dynamical events happen in that state space, similar events will trace out these kind of similar trajectories. So you can think of this as maybe SimH versus its time derivative here. So as a storm progresses, it'll trace one of these curves in this state space, and another storm will trace a similar curve. So the idea is that after we discretize this, we get this kind of cloud of data points, right? And if we're trying to model a particular moment in time, let's say G of T prime here, we're only going to have a handful of other spacecraft available, right? We might have the Themis spacecraft, the Van Allen probes, or whatever for that particular moment in time. That's not nearly enough to to fit our empirical magnetic field model. So the idea is that we then tap into this historical archive of data, looking for other events that are closest to the event we're interested in reconstructing in this finite dimensional state space. So, so you grab all these nearest neighbors, and then you tap the archive for other observations when the magnetosphere is presumably in this similar configuration. And then that is used to then fit our empirical magnetic field model. So another important thing we've been doing recently is we distance weight our magnetic field records based off of the proximity to the moment of time we're interested in. So the moment of time we're interested in always gets the largest weights when the fit is applied. So in a way that kind of mimics data assimilation, because we're giving the moments from the particular event get the highest contribution to the fit. All right, so now we have to formulate our storm and substorm state space. Like I said, we're trying to capture the complex dynamics of the magnetosphere, and we're trying to distill it down to a small finite dimensional state space. So originally, we used this storm state space based off of kind of the Burton-McFarrell-Russell formalism, which related the solar wind electric field parameter, which is VBZ, to SimH and its time derivative. So this is our 3-parameter storm state space that we used to model storms. And then when we wanted to expand this modeling approach to substorms, we simply added the AL, or the substorm index, and its derivative. So we now have this 5D state space for substorms, the storm index, the substorm index, their time derivatives, and then we switch to this VB south parameter. And what we've also done is we've smoothed these data. They're kind of noisy, they kind of bounce around a lot. So to give us a cleaner dynamical picture, we smooth these using these smoothing window filters here, that's what these little bracket notations are trying to signify here. So here is a summary of our current space magnetometer database. So you can see this variety of histograms here, showing that we have pretty ample coverage, especially with the addition of MMS out to about 30 RE now. And it includes data from the advent of continuous solar wind monitoring in 1995 up through approximately the present. So we have IMP8 and GeoTail, the geosynchronous GOES satellites, cluster and polar Van Allen probes, the 5 Themis probes, and then, like I said, we've recently added MMS. And the way we fit the data is the linear amplitude coefficients are fit using the singular value decomposition pseudo-inversion method, which is quite frequently used when in magnetometer data. And then to fit the nonlinear parameters, we use the Nelder-Mead downhill simplex method. A lot of people refer to this as the amoeba method. So basically, this solver is embedded inside of this solver. So whenever the amoeba moves around in the parameter space, we then refit the linear amplitude coefficients. So that's That's how the model is fit. So now I'm going to jump into the results, the science results of these empirical reconstructions. So first we tackled storms. So in modeling the inner magnetosphere, we had to pick a specific resolution for our equatorial current system that captured the dynamics in the ring current system in the inner magnetosphere. And what we see is that the data mining resolves not only these currents, but their dynamics during the course of a storm. So we see that kind of in the more main phase or near the SIMH minimum, the ring current system is highly asymmetric. And actually these two are the same snapshot here. This is showing a 3D picture, and here's a 2D slice of the equatorial current systems. So we're seeing this large enhancement of a partial ring current system, which is then closed both through region 2 field line currents, but also through the eastward ring current system. So we see this asymmetry in the eastward ring current system. So we have this, it's termed the banana current. So we can see we're resolving the majority of the inner magnetospheric current systems during storms. And as this system evolves in time, we can see that during the recovery phase of the storm, we're at a similar SIMH level, but it's now much more symmetric. This is now our much more kind of classic picture of a symmetric ring current system. So moving on, so now that we're pretty convinced that we're resolving the inner magnetosphere, we can use this empirical picture here to estimate what the empirical pressure is from it. So if we assume force balance, we get this force balance equation that relates the gradient of the pressure to this J cross B force term here. And so we can then solve this using this following line integral. So this is just the fundamental theorem of calculus here. So if we assume this force balance equation, we can then solve for pressure by using this line integral. So we have to pick some initial place to perform our integration. So we integrate from, I think, about 10 RE, and then where we can assume this PR naught term is relatively small, and then we just integrate radially inward. And the picture we get is then this picture here. And as we see, we are resolving this kind of asymmetry, in the ring current system, also produces an asymmetry in our pressure distribution. And here's just showing the Van Allen probe's orbit if you map it down to the equatorial plane. And you can see that Van Allen probes is flying directly through this enhanced pressure system that develops during this storm. So here's showing various snapshots of both the equatorial ring current and also the resolved empirical pressure by integrating this ring current system. So you can see during the early main phase, we start to build up a partial ring current system. During the late main phase, we now have this large crescent partial ring current that's quite enhanced. And then during the recovery phase, we return to our kind of classic ring current picture. And we see now we're resolving the pressure associated with this ring current distribution. And you can see that it initially starts to enhance and then becomes quite enhanced, particularly here on the night side, and then becomes much more symmetric as the recovery phase progresses. Well, we want to be able to benchmark how accurately are we capturing this empirical pressure. So fortunately, the Van Allen probes has had a large enough suite of instruments to be able to get a pretty good estimate of what the total pressure was by summing over all these variety of energy channels over the RB Spice and HOPE instruments. And from that, we can reconstruct what the observed total pressure was by Van Allen probes. And that's what I'm now showing here for this July 2013 kind of moderate storm here. And there's two different types of pressures that are computed this way, the perpendicular and parallel pressures. So as you can see, Van Allen probes had a 8 or 9 hour orbit. So during the course of this storm, it made several different passes through the ring current region and through the pressure peak. So you can see the pressure gets enhanced. So that's these blue and yellow dots here, or diamonds, I guess. And we're now comparing that to our empirical pressure that we resolve as I showed here. By basically, flying the Van Allen probes through our empirical reconstructions. And what we see is, while we're at the Van Allen probe apogee, so this is, these two pressures are approximately equal. So we can assume that this is the isotropic regime here. We get very good quantitative agreement, especially it's shown here in Van Allen probes B, just how well the quantitative agreement is between the empirical pressure and the observed pressure from Van Allen probes. Now, as we get towards closer to the pressure peak, we see these yellow diamonds and blue diamonds start to diverge. So the pressure is becoming more anisotropic. So we don't expect as good of quantitative agreement, but we can see by these dashed pink lines here that we still resolve the location of the pressure peak, the radial extent of where the pressure peak is located. So we get quite good both quantitative agreement near the apogee and qualitative agreement in the anisotropic region of where the pressure peak is located in radial location. So moving on to substorms, as I described, the substorm model uses a five-dimensional state space for the data mining approach. So here is the growth phase of a substorm. This is right around substorm onset for this particular substorm. And what we resolve are most of the main features, global features of substorms. So we get this BZ minimum formation in the tail, and along with that, we get this highly stretched and thin magnetotail. And here I'm showing just the thin current sheet portion of our model, and you can see that we get the strong embedded thin current sheet, which is acting to stretch out the tail. Now, 25 minutes later, we get a very different picture. Here's the expansion phase. We now see where we had this BZ minimum is now a large BZ pileup region and a much more dipolar magnetotail, an enhancement of the ring current. And even back then, so this was from 2019, we realized that we were seeing X lines in the tail, but we didn't really know what to think of this result. Are these real, or are these just a result of overfitting? We weren't quite sure, but recently, and one more topic before I move into the X lines, flux evolution. This quantitative global model now allows us to also measure and quantify flux and its evolution during the course of a substorm. So we see during the growth phase, we get dayside erosion of flux, and correlated with that is presumably this flux is being eroded on the dayside due to magnetic reconnection. And then that flux is being stored in the magnetotail lobes. And we see that we are resolving, if we integrate across the lobe here, we're resolving this increase in the amount of flux stored in the lobes. And then during the expansion and recovery phases, that lobe flux goes back down to the nominal level. So this is the effect of magnetic reconnection in the tail, which is converting open flux to closed flux. And along with that, the dayside flux returns during the recovery phase. So here's just showing a movie of the growth and expansion phase. So you can see during the growth phase here, the magnetotail gets stretched. This thin current sheet becomes stronger and stronger until we reach the expansion phase, and then everything rapidly dipolarizes. So we can see we're resolving these main features of substorms. Another cool thing about this is we can also resolve the substorm current wedge. So from our world data, these Bob McFerrin and Fukushima and derived these kind of cartoon pictures of the substorm current wedge. This would later be modified using MHD models, and Joachim Bern had a series of papers describing the substorm current wedge using MHD models. Well, we can now resolve it using our empirical approach. So if we subtract the expansion phase from the growth phase, what we're left with are the current systems that were added during the substorm. And what we end up getting is this empirical picture of the substorm current wedge derived from this data mining based approach. Okay, so moving back on the X lines. So why do we need to resolve the global configuration of the magnetotail? We've recently launched the MMS and the Themis missions, and those missions did a lot to understand the micro scale physics of magnetotail reconnection. So, but the location and the length are kind of the location and the length of the X line are kind of the global scale features. And it's these the global scale morphology of the X line that really determines the energy and flux transport throughout the magnetosphere during storms and substorms. So although MMS revealed many of the details of the microscale physics, the global picture, the global context of the X line is still kind of missing. As a review paper, Nagai put it in 2021, magnetic reconnection occurs in the thin current sheet at a microscale, but the conditions controlling reconnection may be produced at a macro scale. Therefore, multi-scale phenomena should be investigated for further understanding of magnetotail reconnection. So like I said before, we had these hints of X-line formation, but we weren't really sure how well we were resolving this. So here's some of the early models of global X-lines. It really dates all the way back to kind of the dawn of the space era, to the Dungy convection cycle. This was thought to be a more or less continuous process here. And then that would become highly modified with what became the near-Earth neutral line model of substorms. So this is flux is being, as dayside reconnection occurs, flux accumulates in the lobes, it stretches the magnetotail until eventually an X-line forms, magnetic reconnection occurs. And if you would kind of look at the BZ profile along this structure, what you'll see is the X-line occurs at a 0 in the BZ. And then on the tailward edge of that, we would then get an O line associated with this other 0. So I'm kind of using this color. I'll use this color coding in the next series of slides. So what we are looking for in our empirical reconstructions are these zeros that are signifying X lines and O lines. So fortunately with MMS, we now have a way to benchmark whether or not we are actually resolving these X lines. So as MMS was designed to try to, its trajectory to try to fly through these ion diffusion regions and electron diffusion regions where magnetic reconnection is occurring. So these are basically the regions where ideal MHD is breaking down, and this kinetic physics is causing reconnection to occur. So as MMS, as you can envision MMS flying through one of these, it'll see a reversal in the magnetic field. So in the sign of the BZ component of the magnetic field, along with a reversal in the plasma flow velocity. So, and they should be correlated, right? As you fly through these two things should be highly correlated. So here's an example of MMS flying through one of these ion diffusion regions directly observing magnetic reconnection. So we see a reversal in the flow velocity. So these ions were moving tailward, and then they're moving earthward. And correlated with that is a reversal in the magnetic field, the BZ component of the magnetic field. So this is how we know when MMS flies through one of these regions. So Rogers et al. Used this kind of correlated reversals and did a survey of the MMS data and found 12, which they later expanded to 26 ion diffusion regions that were directly observed by MMS. They also required signatures of Hall electric and magnetic fields to be able to confirm that these are indeed ion diffusion regions. So we now applied our data mining based empirical approach to this. We call it the IDR alphabet, since there's 26 of these events that Tony Rogers and colleagues identified, and applied our data mining approach to it. So what we discovered is that of the 26 events, here I'm showing 4, 24 either resolved the X-line location. So you can see here is where MMS was during this event. And this contour here is the BZ equals 0 contour, signifying an X or an O line. And out of the 26 events, 24 were consistent with 24 of the reconstructions were consistent with where MMS observed the an ion diffusion region. So you can see, I mean, some of these are really within half an RE or so difference between the MMS observations and where the empirical data mining based empirical model placed an X or an O line. So 16 are like this, where they're basically right on top of each other. Another 8, we didn't quite resolve it, but we basically got a BZ minimum region, but without fully resolving a BZ equals 0 contour. But basically only 2 events were inconsistent, where the reconstructions were inconsistent with the observations. And both of those had pretty plausible explanations. So this is a good benchmark that we are really resolving the global configuration of X-lines during substorms. And we can now look at the evolution. So we see during this, here's a substorm. Here's kind of prior to onset. We already see out here in the kind of around 30 RE, an X-line has formed. And then by the right around substorm onset, the empirical reconstruction now places that X-line basically right on top of MMS. And then as the substorm evolves, we see this kind of branching so that we get this big crosstail X-line, but then we get these islands of X-lines that are earthward of it. So we get this kind of splintering of this crosstail X-line into these smaller X-line islands. And then as the recovery phase begins, we see these X-lines gradually disappear. So another thing we've been trying to do is I've described our storm model and our substorm model. Well, the problem with these two models is they don't work well together concurrently. And the reason is because the inner magnetosphere requires a different resolution of our equatorial expansion versus our tail model. So we've kind of fallen upon this 3x20 or 6x20 resolution for the inner magnetosphere. And what that resolution does is it nicely describes the eastward ring current system and gives us this nice pressure distribution in the tail or in the inner magnetosphere, right? But the problem is this is, here's a histogram of our magnetometer archive versus geocentric distance. So these are basically the number of data points in each spherical shell. And you can see as we move further out in the tail, and this is a logarithmic scale, we get much less data. So particularly, this is the Themis apogee here at 12 RE. So within inside of 12 RE, we have ample data, but then in the midtail region, we have about a order of magnitude less data, and then we get even less data in the further out in the tail. So the result of this is that we end up with these different resolutions that resolve the inner magnetosphere and the tail. So the problem is the resolution we fell upon for the inner magnetosphere works well with inside the Themis apogee, but it clearly is overfitting data, overfitting to the data in the tail region, because we just don't have as much data out there. So to resolve the tail, we need a lower resolution model, and that gives a really nice, this is what we've been using for our substorm model, a really nice resolution of the tail features. But again, we now are under resolving the inner magnetosphere within side of the Themis apogee, and we don't get an eastward current system, and without an eastward current system, we can't resolve the pressure peak. So we have this kind of problem that the inner model overfits the tail, and the tail model under-resolves the inner magnetosphere. So the question we had is there any way that we can combine these two models so we get a concurrent storm, substorm, inner magnetosphere tail model together? So basically, we would have this high resolution model in the inner magnetosphere, the lower resolution model in the tail. Is there some way we can merge this together to get a coherent picture, but while also keeping the divergenceless nature of the magnetic field and the divergenceless nature of the J field that are kind of built into the structure of our empirical model? And we actually kind of landed upon this clever solution where we basically take our inner model and we take our tail model, and then we just uniformly sample these two models to get our merged model that really gives us the best of both worlds here. So we can see this is a 3x20 for the inner magnetosphere, 6x8 in terms of these expansions. And now we use the 6x20. So this is the number of azimuthal and radial expansions that are in our equatorial current system. You can see by doing this, we now get a merged resolution model, which concurrently describes both the inner magnetosphere and the magnetotail. And so that allows us to investigate the combined storm, substorm dynamics of the magnetosphere. So this is the same substorm I was showing before. So showing the same substorm features as before. So the magnetotail stretching, the thin current sheet intensification, and then rapid dipolarization during the expansion phase. But importantly, we now are also resolving the inner magnetosphere using this merged resolution model and the pressure peak. So we now have a combined storm, substorm model that we can use. So some conclusions here. What I really want to impart, a lot of people are used to using the classic Sig-Yanko empirical magnetic field models. So T89, T96 are some of the commonly used ones. But what I want to impart is that data mining based methods have drastically advanced empirical magnetic field models in the recent years. And that these data mining based models give both a qualitative and a quantitative picture of the global magnetosphere and how it evolves during storms and substorms. We resolve the primary features of storms, like the enhancement of the symmetric and partial ring current and pressure distribution, and the primary features of substorms, such as the thinning and stretching of the tail during the growth phase, and then rapid dipolarization during the expansion phase. And then we also resolve the location and timing of the X-line. So although the X-line was thought to be kind of unsteady and spontaneous, at microscales, this really suggests the global scale of the magnetotail reconnection must be reproducible and correlated with geomagnetic indices and or solar wind inputs. And a cool thing about this is I think it really expands the multi-scale aspect of MMS, multi-scale is in the mission to, by using this data mining approach, we are expanding the scales to include global scales. So, and the last concluding thought is data mining based empirical reconstructions have now really reached the level of maturity that they can now be used to guide MHD models. And that'll be next month's presentation by Harry and Anthony. So please tune in for that talk. And that is all I have. So.
All right, wonderful. Thanks very much, Grant.
Thank you. That was a nice talk.
Do we have any questions?
I have a quick question. So, Grant, thank you. So you are fitting still those models, right? That, same model as sort of like you had the dipole modes or distortion to dipole and all that kind of thing. So do you know that those models are unique, meaning that are they orthogonal to each other? Well, am I making any sense? Do you have any concerns for that when you do the fit?
Right. So they're not.
Right.
Yeah. Our terms and our equatorial current system has orthogonal basis functions.
Mm-hmm.
But as soon as we start combining our thin current sheet with our thick current sheet, like they're no longer orthogonal. So we do have issues with that, where the different current systems try to take away from each other. So yeah, that's a lot of the fine tuning that we've had to do, trying to figure out what initial set of parameters to feed our empirical model with, to make sure that we kind of mitigate as many of those issues as possible. But yeah, that is part of the game we play, is trying to balance how many nearest neighbors to use.
Yeah.
Because if you use too many, you start to smear over the detail that you want.
Yeah.
If you use too few, we start to overfit our model. So it's this kind of juggling game of we want as high of resolution as possible, but as few nearest neighbors as possible. And yeah, so a lot of that is just stuff we've kind of worked out by doing various experiments and kind of landing on this configuration that seems.
Yeah, I mean, it must have taken lots of trial and error. So like, and so I have some thoughts that later at the end, you start saying like, like a tail, you don't have much data, and then, you want to actually, want to fit that separate low resolution data. And also in a fitting, you're combining SVD and then amoeba type of, or greedy methods. So all that sort of, it's kind of like you picked up on the method side, but, impressive result, but, like going forward, maybe you could sort of formalize penalties. So meaning that you don't allow data to influence too much for certain, models, and, so then you don't need to sort of combine these different models, and then you need to, it's a, you have a unified model, like in statistical models, the models that you want to fit to all kinds of data sets, and then, but then, you actually sort of incorporate penalty terms so that you still fit this sort of one fit, and then you kind of take care of this overfit. But that's a suggestion I could talk about. It's very interesting. So I wonder, it might be a long conversation. So I just thought, okay, yes.
Yeah, thanks.
So I think probably other people have questions. Any other questions? Sorry, I jumped because that was very interesting. From audience, please.
No one else has a question. I'll ask one real quick.
Sure.
Is how much do you like? So you're using a shoe magnetopause as your outer boundary. Do you know how much changing that outer boundary condition would affect, the solution inward, like sort of where you're getting your reconnection? How that would affect maybe the inner magnetosphere at all? Would it very much, or no? Because you're still very constrained in those regions by your data.
Yeah, that's a good question. I think what we've noticed, so we focus mostly on the tail, especially our substorm reconstructions. But when we do our empirical pressure, we are integrating from the magnetopause boundary, and that seems to be the biggest of kind of the science results I've showed. I think the biggest kind of shortcoming of this approach is that we don't really know the magnetopause boundary, and it can really impact those line integrals, since we use that as our outer boundary. And we've noticed we've done these experiments where we integrate different directions. So from the tails, from the flanks, and then the radial one that I showed, and it's the day side that has the most variability. And I think it's because we don't really know the outer boundary.
Right, yeah. Yeah, that makes sense. So it definitely makes sense from a integrated perspective, because you're sort of carrying that assumption inward. But it shouldn't really affect at all the magnetic field solution very much in the inner regions, though, right?
Right, I don't think so, yeah.
Cool. Okay, thanks. Any last questions before we call it a day?
I have a quick comment. This is Jeff Stewart. I mostly worked in the troposphere data simulation, but I'm starting to get into the ionosphere. In a separate context, we found that Gaussian mixture models worked a lot better than KNN. Have you heard of that? Are you aware of that technique?
No, I'd be interested. Gaussian mixture models, you say?
Yeah, Gaussian mixture model. So what it does is it's similar to like a k-means clustering algorithm, where you come up with these different clusters, and then you try to characterize their mean as well as a covariance matrix. So then when you want to combine them back together, you kind of know exactly how much of each one you should take. So it can have, it's more powerful and more generalized than a k-means or KNN kind of approach. I don't know if it'll be applicable for your context, but
yeah, I'll look it up, because we've also often struggled with how to optimize our binning parameters, and like how we characterize the magnetosphere. And KNN is pretty simple. So yeah, if there's some more advanced, so I've Googled it. I will look into it. So
yeah, I think you'll find it super powerful.
Well, great. If we have time for one quick question, if anyone has it. No. Okay, not seeing anything. I just wanted to thank Grant again for a really, really great talk and some great discussion afterwards. And then please be on the lookout next month, April 4th, for part 2 of this combined presentations with Anthony Sciola and Harry Arnold, talking about how they can ingest some of these empirical pressure maps into the global NHD modeling. So thanks so much again, and we look forward to seeing you all soon.
yes, thank you.